Good afternoon. I'm David Ferriero. I'm the Archivist of the United States, and I'm pleased to welcome you to the William G. McGowan Theater here at the National Archives to hear Rachel Lance tell us about the fate of the submarine H.L. Hunley. And welcome to those of you who are joining us through our YouTube channel. I'd like to give a special welcome and thanks to Mark Milan. Where are you, Mark? Mark, who is an archivist here at the National Archives in our Old Navy Maritime Reference section, for his help and guidance, and also to the Washington Area Maritime Archivists, Curators, and Historians group, who are also joining us today as co-sponsoring this program. But before we get started, I'd like to tell you about two other programs coming up this week. On Wednesday, December 13th at noon, author Molly Burton will be here to discuss and sign her new book, Finally, A Parade for You, a gift of gratitude for military men and women who served during the Vietnam War. This program is presented in conjunction with our recently opened exhibit, Remembering Vietnam, in the Lawrence F. O'Brien Gallery upstairs. Then on the evening of December 13th at 7, we'll be treated to a concert by the U.S. Navy Band Brass Quintet. Since 1971, the Navy Band Brass Quintet has performed at ceremonies and events throughout the Washington area, including the White House, Pentagon, State Department, and Washington Navy Yard. To learn more about these and all of our public programs and exhibits, consult our monthly calendar of events online at archives.gov, and check out our website or sign up to get email updates. You'll also find information about other National Archives events. And another way to get more involved in the National Archives is to become a member of the National Archives Foundation. The foundation supports all of our education and outreach activity, and there are applications for membership in the lobby also. On February 17, 1864, in the last year of the Civil War, the Confederate submarine H.L. Hunley pressed a black powder explosive against the side of the Union ship USS Housatonic and sank it. Shortly after the Hunley became the first submarine ever to be successful in combat, it mysteriously sank. Even though the submarine was raised in the year 2000, efforts to conserve her only deepened the mystery of why she sank, as the remains of the crew were all found seated peacefully at their battle stations, with no signs of trauma or attempts to escape the doomed vessel. Rachel Lance, a biomedical engineer specializing in trauma patterns from underwater explosions, investigated the various theories to explain the sinking of the Hunley as part of her PhD dissertation studies at Duke University. Her documentary research led her to our holdings here of the U.S. Naval Courts of Inquiry's 1864 investigation into the sinking of the USS Housatonic. Today, we're pleased to welcome her to the National Archives to present the results of her investigation. Rachel Lance holds 2 BS and MS degrees in biomedical engineering from the University of Michigan, and despite remaining a Wolverine at heart, she received her PhD in the same field from Duke University in 2016. And in the spirit of full disclosure, I should mention that I was the librarian at Duke for 8 years, so a special treat to have you here. For the past 9 years, Dr. Lance worked as a proud civil servant for the U.S. Navy, building underwater breathing systems and investigating underwater blast trauma. Recently, she left the civil service and currently performs collaborative research in the field of respiratory physiology with Duke University while working on a book about the Hunley and the science required to solve the mystery, which I hope she will bring here to the audience in Washington when she finishes. Ladies and gentlemen, please welcome Rachel Lance.
Thank you very much for the introduction. As you mentioned, I am Rachel Lance. I hold a PhD in biomedical engineering, and the majority of my specialty and studies have typically been in the patterns of blast trauma as well as respiratory physiology. So the reason that you guys are all here today is to hear about the parts of my PhD that had to do with the Civil War submarine H.L. Hunley. Thank you. Yeah. So while I was doing this research, I was enrolled as a PhD student at Duke University and was simultaneously a civil servant for the U.S. Navy, which is why I was studying blast trauma. So first, to set the scene. Part of the Union's method of attack against the Confederacy was something called the Anaconda Plan. And just like in Anaconda, their goal was to choke out the supply lines, to surround the southern rebellious states and eliminate their ability to access different supplies that would be used not only for warfare, but even to feed the citizens in the Confederacy. Charleston, South Carolina was no exception. By the year 1864, it was the last standing southern port in the Confederacy and was one of the major ways that they were supplying both their military and their civilian populations. The Anaconda Plan meant that ships were stationed offshore just outside of the harbor, and it meant that the city of Charleston was being subjected to nightly shelling by the Union troops and their mortars. One of these ships was the USS Housatonic. It was a sloop of war. It could carry up to 160 crewmen. The Housatonic would soon become the target for the H.L. Hunley. This is a 40-foot submarine. It's barely 4 feet in diameter, approximately circular. And it was hammered out of the wrought iron boiler of a steamship. So this is a recycled piece of equipment. And it was actually built by privateers. This is a really common misconception about the Hunley. People try to append the CSS title, but the men that built it were trying to collect the bounty that the Confederacy was offering in return for sinking Union ships. One of the men who designed and built it was Horace Hunley. Now, Hunley himself actually died in this submarine. He was one of 2 crews that died through training accidents as they were practicing for one of their final assaults on the Union ships offshore. And that led to the submarine being renamed in his honor. This is a contemporary painting by Conrad Wise Chapman. It was done in 1863, so the year before the Hunley's final mission. And it's the most accurate known contemporary representation to date. On February 17th, the Hunley made history. Using a black powder torpedo, which at the time was a stationary bomb, it's not the self-propelled mechanism that we think of today, it approached the Union ship Housatonic and pressed the black powder torpedo against the side of the hull. The Housatonic went down quickly, within 5 to 6 minutes, and the Hunley became famous as the first submarine ever to be successful in combat. But it then disappeared. It disappeared to the tales of history. In the year 2000, the Hunley was recovered. Its final location had been pinpointed in 1995, and it was declared to be the spoils of war, owned by the U.S. Navy, but sent to Charleston on permanent loan for its conservation. Everyone was very excited about this event when it occurred because finally this would provide a solution to the mystery. We had the boat itself. We could get the remaining puzzle pieces to answer the question of why the Hunley disappeared that night in 1864. One of the reasons that the Hunley took so long to find was because it was actually located seaward of the Housatonic. So this was the final position of the Hunley, this little guy right here, and this map is to scale. This was the final position of the Housatonic, where this is the mouth of Charleston Harbor. So the Hunley left from here on its mission, Breach Inlet, traveled outward to the Housatonic, and then drifted out to sea along the direction of the tidal currents from the harbor. Everyone previously, when they'd been looking for this boat, had all assumed that it had started traveling back to Breach Inlet or to the harbor and to safety. But since it was located seaward, it took 150 years to find. Once it was raised, it was placed in a conservation tank in Charleston, South Carolina, where people began to remove the panels and to hope to look for clues to finally solve this mystery. Now, in this picture, you see some damage up at the bow of the Hunley, but careful analysis of the layers of sediment within the boat showed that this damage and a similar piece of damage closer to the stern actually occurred a very long time after the boat sank. So initially, while people thought that this might be the cause of the sinking, it turned out that it was completely unrelated. The only damage that was found to have occurred during or around the time of the sinking was some minor damage to the conning tower, which is illustrated here. You can see on the left of the drawing is a normal viewport, and on the right of the drawing is the damaged viewport. They should be symmetrical if there were not this damaged area. Obviously, that seems a bit smaller than we would expect to actually sink a 40-foot submarine. Now, interestingly, the National Archives has turned out to be, well, not surprising to some of us, turned out to be a really great repository for a lot of information on this historical attack. One of the things that was found that was a major clue was this document here, and I've only shown part of it so that we can see some of the detail. But this is a drawing of a device called the Singer's torpedo. Now, Singer, who is connected to the famous sewing machines, was also designing torpedoes during the Civil War. And his particular design was one of the most common torpedo designs that was in use during combat. So this drawing says very clearly used for blowing up the Housatonic, and it gives us not only a scaled drawing, information on the trigger device over here on the right, but it gives us the size of the charge, which was 135 pounds of black powder. That's a massive amount of powder. This device would have been approximately the size of a beer keg. One of the things that was discovered during the conservation efforts was that the torpedo was still attached to the spar. So the Hunley had a spar protruding off of the front end, and the torpedo as a stationary device was attached to the end of that, which it used to sort of jab at the hull of the Housatonic. Now, when conservation experts got to the spar, they discovered this light gray stuff, perhaps I could have colored that in, is copper. So you have the metal and wood spar, and then you have the copper shards of the torpedo itself. And you can even see the damage where this bolt holding it on, the shell casing was pushed backwards from the force of the explosion. So this is a major clue because it tells us now the exact distance that the boat was from this large explosive charge. We have the archival documents which show us the nature of the charge, which was obviously destroyed during the attack. And then we also have this historical information from the recovery of the boat. So this is a rendering of what the Hunley would have looked like during her final attack. You can see the torpedo down here on the right. It's a little bit cut off, held on with the spar off of her bow. She had dive planes on the side, and that's how she would have controlled her depth. The crew could control those from inside. There's the propeller back here on the stern. She has 2 conning towers, and importantly, those conning towers were how the crew got new air. So they could seal them when they wanted to submerge, but to ventilate the boat, they would need to rise to the surface and open those. The Hunley was equipped with a snorkel mechanism, but by all known accounts, that never really worked and was never used. And in addition, she has ballast weights along the keel, so down along the bottom here. And these ballast weights were actually designed as a safety mechanism. There were bolts attached to these weights that were inside the hull of the submarine, and the crew could turn them to release the ballast weights from within the inside of the hull and send the submarine up to the surface. Now, this looks like a color finger painting, but it's not. I'm going to explain it in a minute. What became really interesting to me about this historical problem was when they started recovering the remains of the crew. As they opened the submarine, the remains of the crew were still inside. But unlike the previous sinkings of the boat, where all of the crew had been clambering to escape, they'd been huddled near the conning towers, they had in some cases looked like they were trying to claw their way out, this crew was stationed exactly where they would have been when they were piloting the boat. So the gray shape is a representation of the submarine's hull, and I've outlined the remains of each individual crew member and given them a separate color. So each person was sitting at his station inside of this boat and made absolutely no effort to get out, to turn the boat, the bolts that would release those hulls from the keel, or even to set the pumps inside that would start to pump out water from the bilge. Now, one thing that I should have mentioned also is that the Hunley was man-powered. So each of these men was necessary because they're seated along a crank handle. And that crank handle was what actually turned the propeller. So that's how we even know more conclusively that each man was sitting at his station, was because they were at their respective crank positions. So this is a quote by one of the friends of the Hunley chairman at the time in 2001. And it says, "Evidence seems to suggest more and more that the final moments were quick and decisive." Now, this is my personal favorite result from the conservation. Lieutenant Dixon was the pilot. He was the commanding officer of this boat. So he was the one that was actually steering and in charge. He sat directly below the fore conning tower, and he had his own little bench here. This is a forward bulkhead, and he would have had instrumentation along it. So you see here part of his skeletal remains. Now, as his remains decayed, some of the bones fell down into the keel. So I've removed those from the illustration, but the ones that I've left are the ones that were locked in place by the intrusion of sediment. So remember from the beginning, this forward conning tower was the first part of the boat that was damaged. And the intrusion from the nearby ocean floor, it created a buildup of silt. So as this buildup of silt entered into the conning tower quickly after the accident, much of Lieutenant Dixon's skeleton was locked in place, as it would have been during his final moments. And you can see he's got his ankles crossed, his arms are slumped over here. This is his left arm and left leg in the lighter color, with the right arm and right leg in the darker color, and his shoes. So he seems to have simply been slumped over to the side. His pelvis has fallen to the keel, but the position of his legs indicate that he was likely still sitting on his bench, exactly where he would have been if he was on duty. So there have long been three major theories that people have promulgated to explain the sinking of the Hunley. The first three were very common, and they've been the first two have been very commonly talked about. The third one is lesser known. I looked at this case, and my expertise is in blast trauma, and I brought some of these details of the case to my advisor, Dale Bass. He and I sort of raised an eyebrow. To us, a lot of these details were starting to look like a blast trauma. So we tentatively added our theory onto the end of this list. So the first theory is the theory of suffocation. That was the first one I want to investigate, and coincidentally, it fell right into my background with the Navy, where I'd been building underwater breathing systems. Now, failure of those breathing systems is a big problem because it means you no longer have an input of oxygen. But what is really interesting is that in any closed volume, you have a buildup of carbon dioxide long before you actually run out of oxygen. So as these men in the crew were exhaling, they would have exhaled carbon dioxide and gradually poisoned their own atmosphere. So this figure is from my first publication about the Hunley, just looking at the theory of suffocation. So this one came out in 2015. And as you can see, the gray line here shows the buildup of carbon dioxide, and the black line shows the depletion of oxygen inside the hull. And the dashed and dotted lines show some variation. So while all volumes have a problem with carbon dioxide burst, I'd also wanted to calculate exactly how much warning time the crew might have had from that, to see if it was plausible that they could have still just lost consciousness anyway before they'd really noticed the symptoms. So I calculated my best calculation for the volume, and then I varied it to see how sensitive the results were to any small errors I might have made in measurements. What I found was that the crew had about a 30-minute air supply before they would have had very painful and uncomfortable symptoms from carbon dioxide. And along with that, they would have had an absolute minimum of 10 minutes, even using the most conservative parameters I could think of, before they would have had risk of loss of consciousness. So if they're in there and they're physically uncomfortable and they're struggling and they have at least 10 minutes, they've made no efforts, once again, to try and save themselves or bring new air into the boat. The attack did occur while the Hunley was on the surface, so they could have easily just opened the conning tower hatches. Coincidentally, we have another example from history that ties into this exact scenario. The HMS Thetis was a British submarine that was sank in the early 1900s. So the Thetis, interestingly, had about 967 liters of gas per person. The Hunley varied from that by only 2%. So in the test case of the Thetis, we have almost exactly a representation of the amount of volume per person as we do with the Submarine H.L. Hunley. Now, the Thetis is relevant for two reasons, because first of all, they recovered it, and the volume is similar. And second of all, because scientists were aware of the sinking at the time that it happened. So they conducted experiments on themselves to see what would have happened first in that closed space. So first I've put up here a quote, and it's from an archival document at the UK National Archives. And I used a secondary source, so I cited that as well. But carbon dioxide poisoning brings on an agonizing end. Eyes bulging, gagging like dying fish out of water, the men huddled together for a little human comfort until a welcome death ended their suffering. So my point with this quote is not to be graphic. It's to give you some idea of the discomfort level involved in carbon dioxide. As the scientists were performing their experiments as well, they described sensations of choking, of gagging, of panic, of psychological and physical discomfort. They actually could not complete their experiments because they kept repeatedly having to purge the carbon dioxide from their chamber that they had built. On a personal note, I have experienced high carbon dioxide. It's extremely uncomfortable. So for me, that eliminated the suffocation theory, because if you have 10 minutes in that level of symptoms, nobody is sitting there peacefully. Next on the list was the lucky shot theory. We know from the archival document, which was the U.S. Navy's Court of Inquiry. So the U.S. Navy performed this Court of Inquiry, interviewing the crewmen of the Housatonic after it was sunk to see if something could have been done to save it. They wanted to know, basically, was it just this submarine that was to blame, or did the crew make a mistake? So several of the crew testified that they were firing their personal firearms at the Hunley as it was approaching on the surface. They saw it coming, but it was already too close for them to train the heavy artillery of the ship downward at the correct angle. So the lucky shot theory states that one of the men, such as Captain Pickering, who was firing his musket, managed to hit this submarine and cause damage in such a way that it led to the sinking. Now, just as a refresher, put back that illustration of the conning tower. This was the only damage that was known to have occurred at or close to the time of the sinking. So obviously, the best way to test this was to befriend a Civil War reenactor. It worked very well. So on the left is an image of my friend Chris Kelly. We became friends through this project. And he has recently moved, but he was a Civil War reenactor in the state of North Carolina. And this is a group of people who has very diligent attention to detail and the authenticity of their reproductions. So the actual time period rifles are no longer considered safe to fire because of changes that have occurred to the metal, but he had a period accurate reproduction. So the image on the right is my fearless undergrad, Henry Warder. He was very involved in this aspect of the project, and he was one of the people who was firing the rifle at test day. So I wanted to give him appropriate credit. And here's what we found. So me and my co-authors, my colleagues, used two different groups of cast iron samples. The picture on the left is from the thinner samples. And as you can see, it's completely fractured. So these samples, every time, were completely destroyed. And then as we began to increase the thickness, the way that the cast iron began to fail was by having these bullets completely and cleanly penetrate. So we would get some plastic deformation at the edge along the site, but in general, you would just see this bullet penetration with some fraying around the edges. Again, the archives came into heavy play here because we had questions about whether or not our cast iron samples were accurate. I mean, we've got them from 150 years ago. So do the modern ones replicate what was happening then? So these diagrams are actually, I love them so much. They're from a book in the National Archives where the Confederacy was performing testing to build armor for their ironclads. So the famous Battle of the Ironclads, this record group documented all of the testing that they performed on cast iron plating to see which thicknesses would best protect those ships. So what was really interesting to me is that their damage matched our damage. So you see these samples where there's clean penetrations and plastic deformation around the edges. Now, if you compare those, the historical samples with the clean penetrations, the modern samples with the clean penetrations, neither of those matches the damage to this conning tower. So in this, you don't see a clean bullet hole, and you don't see a widespread fracture like happened with the thinner samples. You see this small area of damage that is larger, definitely larger than a bullet, but did not propagate further in the conning tower. We wanted to also back this up with some careful analysis. So Henry Warder, the fearless undergrad, helped implement a system of calculations. So we created a mathematical model for this ship. How quickly would the Hunley sink? How quickly would it drift? Could it sink from a bullet hole and end up in the location where it was found? So this was obviously a really important question, because if the lucky shot theory is true, it would have started sinking right away. The crew would not have been able to take preventative measures. What we discovered was that, according to our analysis of the tides and currents that would have been happening in Charleston Harbor around that time, the Hunley needed at least 14 minutes to end up where it was found. And that is a minimum. There's since been a lot of modifications to Charleston Harbor that all increased the amount of current. So this was actually really good, because a couple months after we came up with that, the Friends of the Hunley also published that they had calculated it would take 13 minutes. So this number is not a question of debate. Everybody agrees that it takes at least that 13 to 14 minutes for the boat to end up where it was finally found. In addition, we've calculated that for it to sink from a bullet hole, it would take at least 58 minutes. So why were they not pumping out the water? Why were they not trying to get out of the boat? And if it sank from a hole the size that was found in the conning tower, it would have sank in less than 5 minutes. And that number also was then confirmed by the University of Michigan. They were actually looking at a broken pipe, but they used a comparable volume. So again, that number is not even being debated. So if that were true, it would have, again, been much closer to the Housatonic. It would not have had the 13 or 14 minutes to reach its final position. So for me, at least, that conclusively eliminated the lucky shot theory. So the third theory that I'd like to talk about is the theory of concussion. Now, this has recently been somewhat confused with the blast trauma theory. The theory of concussion states that these men, inside their very close environment, this thing is under 4 feet wide and just over 4 feet tall, when the explosion went off, the ship obviously rocked in response. That's a lot of force. So it stated that they hit their heads in such a way that they were either knocked unconscious or killed. Now, there were no signs of skull fracture or necrovertebral trauma to the crew inside, but there is a window where you can have loss of consciousness before you get skull fracture. So this theory was the subject of modeling by some Navy colleagues of mine from a different base. So Carderock and Indian had approached this subject by looking at these dummy models, and they simulated the explosion computationally. And they found that while the dummies were moved around a little bit inside the boat, they did not necessarily hit their heads hard enough to cause any kind of significant trauma. So this theory, which is blunt force trauma to the head, they eliminated as no longer plausible. So the last theory is the theory of blast trauma. And one of the things that has been the most difficult for me about this project is the level of misconception that many people have about how explosions actually work. So when preparing for this talk today, I thought that obviously the best way to explain this would be to just show several videos of explosions. So here is a video clip of a movie where there's an explosion that occurs. And this is the conception that most people have. The blast goes off, There are bad guys. The bad guys get thrown. Here's some more bad guys getting thrown because of the first explosion. So this is actually a really common trope in cinema. Originally, I was putting together a clip reel with multiple, but it escalated out of control. It was 13 minutes long before I really reined it in. So I went to one clip instead. So this, because of its representation in media, is how most people think of blasts and blast trauma. The reality, while explosions are fun, is actually far less dramatic. So this is an actual explosion. What's important to note, and this will loop several times, what's important to note about this is that this dummy is freestanding. He weighs 180 pounds, and he is in no way attached or braced against the floor. So the other thing that's very important about this clip is this dummy is in a range of exposure that has a 100% chance of lethality. So there is no surviving this blast. The blast is occurring just off screen. It's C4. You can see he's almost kissed by the fireball. And as it starts, you can even watch the shock wave pass over him. See it right there? It's going past. So some of his fabric and his clothing gets moved, but the dummy itself, we call it translation. The dummy itself does not get translated at all. And that's far more representative of a real blast trauma. Typically, if people are in a fatal blast range, they simply fall where they stood. So there are two main types of injuries that would occur. So blast injuries are divided up into categories, and what I'd like to emphasize is what I'm talking about is something called primary blast, which is the injury from the pressure itself. So we're not talking about shrapnel, we're not talking about flying debris. We're not talking about any type of blunt force trauma. It's just pressure waves. So that's what separates it from that earlier theory of concussion. We're not saying people are getting hit. It's just a pressure exposure. The first way that people can be injured from this is by traumatic brain injury, which is a really big topic lately, but that's from blunt force trauma. It's separate. And in this, small deformations rupture blood vessels and neurons, but they leave the brain largely intact. So when you look at the brain of someone who has a traumatic brain injury, it still generally looks normal. In severe cases, you sometimes get diffuse bleeding or hematoma on the surface of the brain, and that can be a hallmark of it as well. So what's really interesting to me about that is that's consistent with the Hunley findings. These remains were underwater for 150 years, and when they pulled them out of the ocean, their brains were still inside. The brains were intact. Some showed a diffuse staining across the surface. Now, that's very much a grain of salt finding because we don't have a huge body of evidence on what the effects of 150 years of salt water are on the human brain. So it could be from multiple things. It was not conclusively identified as blood, but it could be consistent with a blast-induced hematoma. One of the more common and pernicious effects of blast is something called blast lung. When you have a shock wave, it typically travels through the tissue of the human body at about 1,500 meters per second. Because the human body is largely water, so that's about the speed of sound in water. The problem is when it hits spaces that contain gas, like the lungs or sometimes the abdominal tract, it has to slow down. The speed of sound in air is a lot slower. So it goes from about 1,500 meters per second to about 30 meters per second. And all that energy and momentum has to be transferred somewhere. So I didn't want to show you guys pictures of lungs. I thought not everybody would appreciate that. But here are some x-rays that show the pathology. So on the left is a clear x-ray. These are normal, healthy lungs. And you can see some intact blood vessels. But otherwise, you can pretty much see through the lung. It's black. On the right is an x-ray of pulmonary blast trauma. So this was, I don't believe this, no, this was not a fatal case because it's about recovery. But it was a fairly moderate to severe case. And you can see this white cloudiness that's filled the lungs. So what that means on an x-ray is typically that there's some kind of liquid in there. In this case, that liquid is blood. So the energy from the blast wave has ruptured the blood vessels on the surface. And that's the hallmark of blast trauma, really. So The second obstacle has been convincing people that blasts can, in fact, go through surfaces. The physics of shock waves are incredibly complex. I decided to spare you all from them. If anyone would like more information on that, please feel free to email me. We can be best friends forever. I will talk about it for days. But my favorite graphic representation of the physics has actually come out of Clemson University. So this theory of transmission is about 70-ish years old. It was first developed by a man named G.I. Taylor, who, if you're a super nerd like me, is a pretty famous name. But Clemson did this amazing simulation. And this is a quantitative model, so they actually implemented these equations and did the calculations. So it's not just a pretty graphic. I've modified it a little bit to make it clear. But basically, you have a shock wave, or in the case of black powder, a strong pressure wave, coming in from the left, and it hits this structure. So for us, this is water, and this structure is the hull of the Hunley. Now, on the right, you have ambient air, which would be the inside or crew compartment. So as that blast wave hits the structure, it travels inside. So you get propagation through that wall. And then on the other side, you can get an induced secondary blast wave. So this is it's a concept that's been known to occur for a long time in the blast trauma community. It's something that's studied when people are designing ballistic vests. It's even been measured and proven to occur inside the protective bomb suits that explosive ordnance personnel wear. But it's never before been shown to cause an injury or fatality because you do get a very strong reduction in the force of the blast. But again, like, this is the computational model showing that this is possible and that this works in theory. So now we go back to Dixon's remains. Does this picture look different to everyone now that we know more about blast trauma? Because it really does to me. This to me looks like we have our first case of transmitted blast fatality. In addition, this is one of my favorite facts about the Hunley mystery. Dixon carried a pocket watch. That pocket watch stopped because it was broken. It did not wind down, and it stopped at 8:23 p.m. Now, the attack was reported to occur in the archival document that was the court of inquiry. It was reported to occur between 8:45 and 9 o'clock p.m., but the Union and the Confederacy kept time slightly differently. So 8:23 p.m. to a Confederate was 8:45 p.m. to a Union soldier. So this watch stopped about the exact time of the attack on the Housatonic. Now, that could be coincidence. There are other things that could have broken it. It could have broken from water intrusion. It could have been jostled around during the blast as the boat shook. I personally am itching to get some antique pocket watches and blast them because I think that is also a plausible explanation. So if anyone has pocket watches, they don't mind being broken, I'll be happy to bring the explosives. All right. Now, one of the big question marks for me when I started investigating this mystery is that there are two eyewitness reports that say they saw a blue light on the water after the attack on the Housatonic. This is important because the blue light was supposed to be the Hunley signal that it was victorious and heading back to harbor. So from my mind, this looks like a blast trauma. This smells like a blast trauma. But if they survived and they signaled, it can't be a blast trauma. So I decided to do a little bit more investigation into the nature of these eyewitness reports. The first one is from a man named Robert F. Fleming. His name is actually spelled wrong in the court of inquiry, so I've corrected it here, based on his actual service records. So when the Canandaigua got astern and lying athwart of the Housatonic, about 4 ships lengths off, I saw a blue light on the water. So this is a man who, after the Housatonic got subjected to the torpedo blast, all of the crew were scrambling for survival. This is Charleston in February. It is the South. I know it's not cold to people in DC, but the water temperature at the time would have been about 50 degrees. And the air temperature, it was supposed to be a notoriously cold winter, would have been in the upper 30s. So in the upper 30s, when you're exposed, when you've been in the water that's 50 degrees, he's been clinging to the fore rigging of the Housatonic So the Canandaigua was the ship that came to rescue them. After the Housatonic went down, all of the men scrambled into the rigging to reduce their exposure to the frigid water, and they hung on there for dear life until they got rescued. So that is what I think is the most interesting, is because by all accounts, they were physically exhausted by the time they were rescued. On top of it, once you comb through this court of inquiry more carefully, there are a lot of inconsistencies in the report. So I've pulled out 3, and these are just 3 separate sailors who are describing how the Hunley attacked. So the first one says it came at right angles in the middle. Second one says it came about 45 degrees from the front. And the last one said it came obliquely from the keel. So these are completely disagreeing accounts. And I'm not at all trying to cast aspersions on the credibility of these people. But what I think that this shows is that human memory is very fallible. And that's especially true when you have recently been blown up. These were men who were in a large amount of distress. They were clinging in the water. They were dealing with exhaustion and hypothermia. And on top of it, there were the Housatonic was capable of carrying 160 men. Only 1 reported any sighting of a blue light. So I personally think that this is a suspicious account. If there were really a blue light, if there were really this signal, then it would have been reported by multiple people. So the second one was by Lieutenant Colonel Dantzler. He was positioned at Battery Marshall, which is I've marked with a star, and you can still see this box over here, which is the wreck of the Housatonic, and the Hunley were in there. So he was supposed to be on the lookout for the Hunley to return, and he left this quote. As a recording of that night. So he says, "The signals agreed upon to be given in case the boat wished a light to be exposed at this post as a guide for its return were observed and answered." So people have interpreted that to mean that he saw the Hunley's blue light and he responded by lighting a signal fire for the Hunley to come home. The problem is he's the only one that reported seeing the blue light, and there's no record of the signal fire being lit, at least not that I was able to find. So what I wanted to do was carefully evaluate, is it even plausible that he could have seen it? He's a distance of well over 6 miles from the wreck site. Here's a view of the moon over Charleston Harbor. Now, the moon on that night would have been 3/4 full, so this picture is about accurate. It's a little bit brighter than the human eye normally sees because this photographer is using a long exposure time, but this biases us in the favor of being able to spot the Hunley. So that's a good thing for our purposes. So you see the reflection of the moon on the water. Now, in the human vision, if you draw a 360-degree circle around the head, the moon takes up 30 minutes of that circle, so degrees, minutes, seconds. Using that calculation and the fact that the Hunley was 40 feet long, that's what it would have looked like to Dantzler from Battery Marshall. And I even rounded down. This is calculations assuming that it was 6 miles away. Now, in case you missed it, that's without the Hunley. That's with the Hunley. It's right there. Now, also in this picture is the blue light signal. Again, not extremely obvious. There was a Civil War reenactor named Chris Rucker who reconstructed the pyrotechnic blue light and posted all of his demonstrations on YouTube. They're actually really interesting. I recommend you look them up if you have a minute. But he created a large signal flame. It was about 3 to 4 inches in diameter, which is the upper end of what we could reasonably expect them to be carrying in their small submarine. The light from his signal was approximately 6 inches wide. So when I was creating this picture, I created the light to be 10 to 12, or 6 feet wide. I apologize for that. No, his light was 6 feet wide. You could see visibly for 6 feet. When I created this picture, I made it 10 to 12 feet wide. Again, I was trying to bias this in favor of letting Dantzler find that Hunley. And as you can see, the effects are not very dramatic. There would have also been additional ships. The Housatonic just went down. The Canandaigua was coming to rescue her. The Union was aware, and there was activity in the area. So this is a quote by Jacob Newton Cardozo. He did write it down after the fact, so it was 2 years afterwards. But he reports that the lights never appeared. So again, there's a single report at a distance of over 6 miles with a reflection of the moon and ship activity in the area. He may have been right. He may have had sharper eyes, but I personally was not convinced. So the obvious next step for me was to start blowing things up. It's what I do best. So unfortunately, I had neither the time nor the budget to build a full-size submarine or the facilities. So what we did was we built a scale model. And this is a very common method of experimentation with explosions. You can often scale things down if you do it properly. So I brought the USS Tiny with me today, and before you ask, it was named that at 4 a.m. in the lab on a very long day. So it was meant to be more whimsical than historically accurate. But it's a perfect 1/6 scale model. So it's 6.5 feet long. And there's instrumentation ports. So this hatch at the top has ports that allow me to put blast gauges inside the boat. You can see these fill valves at the front, or the bow and the stern. It has working ballast tanks inside. So we were able to fill the ballast tanks with water to the correct level to mimic what the Hunley would have used. Now, off the bow is a threaded port, and that's where we attached our scaled spar. I wanted to make sure that was removable because I was anticipating we would break a few. The original Hunley was not white. I did that for visibility reasons for when we were filming it. Now, unfortunately, I was going to show you a video of one of the blast experiments, but we had some technical difficulties with it here. So there are sources where you can find that online through news articles about this publication, but I couldn't get it working for you today, and I apologize. But one thing that was interesting was we had some limitations that were placed on us by the Bureau of Alcohol, Tobacco, Firearms, and Explosives. And they were actually extremely helpful during our testing. One of their agents even volunteered his time to come test with us. But they asked us to restrict the charge size, and they were being reasonable about it. It was a fair request. But what that meant was that we ended up with a charge that was much, much smaller than what the Hunley would have actually used. So that's a limitation to the experiment. One of the reasons that I know it was so much smaller was, again, because of archival research. So that plays a role once again. This time I was at the Hagley Archives. So this is a museum in Delaware that's exclusively dedicated to black powder. And this is a test point that was performed in the early 1870s. So they had the exact same type of black powder I would have expected to be used for the Hunley, and they had the exact same charge size. So they were firing shots out of a rifle as part of measuring it, but they also managed to get pressure measurements. So there's 24,200 pounds per square inch of pressure. It's approximately 500 times what I managed to get. So I'm quite confident that my charges were severely undersized based on the archival results. Now again, I apologize. I do have to show you some physics. But so these are the results from the blast test. These are two different mechanisms. The one on the left is a live explosive charge, and the one on the right is something called a shock tube. But what these both show is that there's propagation of this blast inside the hull. So you see a relatively straight line. It extends further than that. And then once the blast wave from the charge passes into the water, you see this blast wave passing into the hull of the boat. And so waveforms of this shape have already been tested and shown that they're still injurious at the same levels as normal kinds, which are much smoother. So that confirmed the theory that in this scenario, the Hunley was experiencing some degree of transmission of the explosion into the hull. I wanted to be extra sure. My advisor wanted to be extra sure. So we decided to do a worst case scenario. This image is a steel plate. It is 5/8 of an inch thick. That is thicker than the hull of the Hunley, which was 3/8 of an inch thick. So we biased everything against ourselves. This tube that you see jutting out from the end is part of what is called a shock tube. And these devices use compressed air to simulate the effects of an explosion without all the muss and fuss of actual live explosives. So what you see on the right are the results. Oh, sorry. You see the waveform from the shock tube, and it's in red. There's some reflections here. So the actual waveform is in red. And then we had gauges behind the plate. So again, 5/8 thick steel. There's no pressure, and then there's transmission of the shock. So again, this confirmed the Hunley's hull with 3/8 of an inch could definitely be transmitting this blast. Based on the calculations of the experimentation, the Hunley was transmitting about 8.4% of the peak pressure of the blast that would have been in the water. So this graph looks a little odd. As I mentioned, this theory is about 70 years old, so I plotted it to keep it consistent with what people have done for the past 70 years. But there's the red line, that's the Hunley, and then you draw a line over to the left and show the transmission percentage. Okay. So because the charges were so undersized, this was a limitation of the paper. So I had to use something called relative equivalency, and this is not a perfect method. I do need to fully disclose that. It tends to be very sensitive to the exact scenario where you're using. But what it basically means is if I have 1 pound of black powder, how much TNT is that equal to? So if I have 1 pound of black powder, is it 0.6 pounds of TNT? Is it 0.4 pounds of TNT? So again, it's kind of sensitive to the way that you set things up. But I took all the values that I could find from the literature where people had measured this, and I put them inside of a gray box. So this gray box is the reasonable range where the relative equivalency should fall. And the red dot is the most common value. It's the median value. So the red dot, and then it's at 8.4% transmission, is my best calculation for what the crew of the Hunley would have experienced. Now, this is really important because you see the risk lines. So the one on the left is pulmonary fatality. So here's the 90% risk line, and the men showed about an 85% chance of immediate pulmonary fatality. So that is per crew member. So the odds that it's possible that 2 or 3 of them survived, but even then, the risk of injury, they were above the 99% risk chance for pulmonary injury. So these are personnel who would have likely had rupture of their lung surface. They would have had difficulty breathing. They would have difficulty getting oxygen to their limbs. So the value for the TNT relative equivalency, like I said, it's not perfect. But if you look at the ranges where they would have had to be to escape all injury, it's below what is considered reasonable for explosives. So it would have to be like below, I believe it's 0.09. I don't have my notes in front of me. I apologize. But below 0.09 for them to have a reasonable chance of less than 90% chance of severe injury. So to me, even though this is not the preferred method, I would prefer to do full-size charges. 0.09 is, I want to use the word preposterous. I don't think I can do that as a scientist, but it's not a realistic value. So here's the same curves for risk of traumatic brain injury. They would have had about a 31% risk of fatal traumatic brain injury immediately from the blast. So again, that's consistent. Some of these crew members had that staining on the surface of their brain. And it's not conclusive, but it is at least consistent with the theory and what I was showing through these experiments. This is not the Civil War. This is the Battle of Midway. But the reason that this is up here is because when I started this project, I had been studying what happens to human beings as they're in the water unprotected. And a lot of my case studies were coming from World War II. They were coming from men who had been in the water, and a depth charge happened to go off near them, and they would suffer this pulmonary trauma. So that was always on my mind. Like, why weren't submariners in World War II experiencing any of this? So that was one of the first things I investigated, and it didn't make it into the final paper, but it was pretty neat, so I thought I'd show you guys today. So here's that same curve. So the Hunley is this red dashed line up here. World War II submarines, their hulls were 7/8 of an inch thick. So they're 7/8 of an inch mild steel. So as they were designing these submarines to go to deeper pressures, to avoid being crushed so they could be stealthier, what they accidentally did was protect themselves against this same phenomenon of blast transmission. So with the 7/8 inch thick steel hull, this star shows where the World War II submarines would have been on this same plot. Now, it goes from 8.4% with the Hunley to 0.18% in World War II. So yeah, I did do some math on it, in case you're wondering. So a 300-pound TNT depth charge, which would have been the most common type of depth charge used at the time, has a kill radius for submarines of less than 100 feet or 30 meters. So I said, what if someone is exactly on the outside of this kill range? They're as close as you can be without actually sinking the sub. So for that to occur, they would have had about 2.4 kilopascals or 0.35 psi transmitted into the hull of the boat. Not only is this well below the threshold for pulmonary blast injury, we can actually draw a relationship to sound. So that would be about 145 decibels, and that's about the sound of a gunshot. So that's actually really neat to me because it's consistent with the testimonies of World War II submariners who are explaining what it's like to be depth charged. So now I'd just like to recap. We have the H.L. Hunley. We have our 135-pound torpedo. She goes up, presses it against the hull of the Housatonic. The Housatonic sinks within 5 minutes. They were firing at her, but none of them caused a large area of damage, and it is inconsistent with where she was finally found. As they brought her up, they discovered that the remains were still sitting in place. And as we know now, blast does not move you, it does not throw you, it does not break bones, it does not destroy the material of your brain. That's exactly how the crew was found. So again, there are some limitations based on the scaling of the charge. I would love to build more full-size charges. But to me, this theory is the final explanation of what happened to the crew and why that ship drifted off into the night in 1864. Thank you. Thank you. Yeah, I had to fiddle with the font size on this one for a while. One thing that I always try to really emphasize, I'm the first author on this paper, and it was part of my PhD, but no one stands alone in science. I would have been just a sad person sitting in a muddy pond by myself without the help of a lot of other people. And our whole project budget was $4,000, so every one of these human beings is a volunteer. So I owe them all a huge thank you, and I've reached out to all of them privately as well. So I wanted to make sure I put them up here for you guys. And if we could ask for questions, if people could go to the microphones on the side, that would be very helpful. But it's time. Oh, this is one of my favorite photos. It shows some more unintentional blast trauma. So, yeah. Yes.
Okay, two questions that are minor throwaways. Could you explain why the Confederacy and the Union had different times? And was that just in the Charleston Harbor area? And second, why did the ATF want to limit the size of the blast?
So the first one, I'm afraid I don't know the answer to that. I do know that it was extensive throughout the Confederacy. It was not just Charleston Harbor, but I'm not quite sure why they had different methods of keeping time. I would speculate without any foundation that it's similar to why some states have daylight savings time and some don't. The ATF asked us to limit the size of the blast just for safety reasons. So we were already generating fairly large explosions, but the explosion that would have been generated with the Hunley was quite dramatic. Yeah. So, hi. Oh, yeah.
Well, for one thing, I can address very quickly what you mentioned on why there were differences in times. Navy ship time was based on Naval Observatory here in Washington, D.C., wherever the ships were in the world. So hence the Housatonic was on Washington, D.C. time. Dixon's watch would have been on local Charleston time, probably based on setting it on a sundial with the position of the sun. Hi, I'm Robert Nealon. I'm the head of underwater archaeology for the U.S. Navy. I was the principal investigator for the recovery of the H.L. Hunley. You know, I think you did a very good job of telling the story of the Hunley. What a wonderful job of talking about it and telling that story. As you know, there is a difference of opinion between the Navy. The Navy has done research on the explosion of the Hunley. Naval Surface Warfare Center at Carter Rock, which you mentioned here, as well as I think the University of Michigan as well, too. Anyway, we have come up with different results that counter that. There has been a full-scale test of a 135-pound black powder charge detonated Aberdeen's testing pond. And our conclusions or the engineers' conclusions are different, that there would not have been any traumatic injury to the men in the submarine on the Hunley. That probably there would have been some heave on the motion of the submarine, but it would not have injured the crew. Anyway, I just wanted to, at least let it be known that there is a difference of opinion on some of the scientific testing for that.
Yeah, so as a scientist, I really actually enjoy scientific discourse and discussion of different theories. What I think has been really interesting is the continued conflagration of those two theories. So I've actually collaborated with many of those scientists multiple times. I know several of them very well, and we've discussed this. I don't want to speak for them necessarily, but their project was on the theory of concussion or blunt force trauma. And I do agree with the results. They're fantastic blast researchers, and they're very well informed. And they were not studying the propagation through the hull. So, yeah, I think it's bordered on a little bit inappropriate that continuing confusion has been used to try to refute my results when it actually studies a completely different theory. So, yes.
Two questions. One is the conning tower. Is there anything from a perspective as far as blowback? I'm not clear on what the theories are, and that the conning tower was outside or above the water surface, and the distance between the conning tower and the ship itself when the explosion went off, that items that were blown into the air versus the sonic that was occurring underwater. Is there anything from that perspective that was tested? And also, do you know of anything, this is very famous, that the Union was doing, whether that was somebody freelance or other, as far as submarine technology at the same time?
Yes, so to answer your questions in reverse, the Union was also working on submarine technology. They had at least one prototype called the Alligator, but it was less successful than the Hunley, obviously, and I can't remember exactly how it was lost, but it was not ever really used in combat. But both sides were definitely working on this idea and this concept. The first real submarine technology was actually used in the American Revolutionary War, something called the Turtle. So, and then as to the damage for the conning tower, I don't know. I would guess it's unlikely, just because of the directionality of the blast and the fact that it's coming from underwater and the conning tower is above. But I don't know that that's ever been specifically tested. I haven't specifically tested it, so yeah. Okay, any more questions? Great. So if you guys would like to come up and see the model, please feel free to do so.